We continue our study. Now we are in chapter 5, and in chapter 5, we are focusing on the stability of laminar flows. And today, uh, uh, why stability is very important, because so we are now discussing about boundary layer. And let's say we have an object. So let's say we have uh, a flat plate like this. So and then we have a boundary layer here. And first we are discussing about laminar boundary layers. So laminar boundary layers mean 100% laminar boundary layers on our object. However, laminar boundary layer, so it's totally dependent on the velocity. So if the velocity keep increasing, means at certain point they will change to turbulent. So in chapter 6 we will learn about turbulent boundary layer, but now we are at we will focus on the transition period. So means that if we have an object here, so and then when the velocity, the free stream velocity increase, so might be we have a laminar here. So and then might be we have a transition here before it convert into fully turbulent boundary layer. So now we are focusing on the transition here. So in undergraduate, so we assume that transition is very small and we don't focus on what happened in transition. So but in this course, in this subject for postgraduate, we try to bring you a few ideas how to analyze what happened in the transition region. So one of them is about the stability of laminar flows. So what is the meaning of the stability here? So the idea is, let's say we have something like this. For example, we have a flat plate here, and then we have a free stream here. So and then let's say it will create a laminar boundary layer. So and then the stability means that if we put some disturbance here, for example, we put a wire here. So if we put it very near to the starting point here, we found that the laminar here will flow on the object here, and it still continue the laminar boundary layer. So means the existence of this object is actually not change the laminar boundary layers into the turbulent ones. So means that the situation here is quite stable. Means we give the flow a little bit disturbance, but it's not changing the flow. However, okay, let's say for example in this situation, so the laminar boundary layer will change to turbulent boundary layer at this point. So and then again we put a same wire here, so a little bit ahead from the transition period here. So means that maybe because this is very near to the transition area, which is here. So maybe after the flow on this wire, so it will change into turbulence. So means by adding the wire here, so we could make the turbulent boundary layer a little faster compared to the common situation. So first, we need to understand what is the meaning of stability here. So stability can be described as a physical state which could withstand a disturbance and still return to its original state. So this is the common meaning of a stability. Means, for example, here, so whether if we put a disturbance here, I mean we put some object here, so the flow will flow around that, will flow through the object, and then it will remain the laminar boundary layer. So means that the stability of laminar boundary layer at this position is very good. Then for here, if the laminar boundary layer flow on this disturbance, so it's changed into the turbulent. So means the stability it might be not so good at this point. Okay, so the simple idea about the stability can be shown like this. For example, if we have a curved area like this one, so and then we have a rolling ball here. So if we we push this ball at certain force, so the ball will moving like this one, but at the end it will stay to its original position. So this is means that this situation is a stable one. So this is the very unstable condition, because with a slight disturbance here, if you just uh, disturb the ball slightly, so the ball will move to another location. So and then the C here, we could it the neutral stability, because it can be the ball can stop anywhere. So it's depend on the force that you give to the ball. And for D here, it can be described as stable for small disturbance but unstable for large one. So this is the very common analogy to describe the stability of one things. So but if you want to relate the stability of boundary layer, so I already explained about that just now. So you just imagine that if you put something that that something is actually depends on you. For example, we make a wire, a trip wire to create turbulence, but some people will create put a very rough surface on certain plate to create to enhance or to make turbulent boundary layer faster compared to its original condition. So and then I would like to discuss about the word transition here. So transition means the phase change, the change here. As stated here, the change over space and time and a certain Reynolds number range of a laminar flow into a turbulent flow. So the common experiment conducted by Reynolds. Reynolds is a scientist. So it create using a see-through pipe and a dye. So mean an ink here. So for example, we have a pipe here. So and then when the flow, the water flow inside this pipe, so we release an ink here. So we could imagine that for the first if the velocity is quite stable, if the velocity is quite low, so means that we found that our dye filament here will flow as a one thin line. So and then if we increase the speed, we found that the ink will flow with one thin line like this, and then it will become rough here. So and then if the velocity keep increasing, so we found that our ink here will flow as one thin line here, and then it start to disappear. So we found that the changes of phase mean the changes from the straight line here to the chaotic pattern here is the transition between laminar. So this is laminar and this is turbulent. So this is the transition. So and then about the transition here, okay, for high velocity, so maybe the transition period or transition length is shorter. So if the velocity is intermediate, so the transition means will be occur at certain length. So what is the meaning of transition? Means they have both. They have laminar and they have turbulence. So for example, here in this transition region, for example, maybe this is the transition region. Maybe we could assume that at this point, so might be turbulent is 10%, So at the middle here, maybe turbulent is become 60%, and right just here, so the turbulent is maybe 95%. And then suddenly at this region, the turbulent is now 100%. Okay, that is the situation, or general ideas about what happened in transition region. So and then, so how to determine this one? We need to determine it by Reynolds number, the common one. Say, and again, you must be careful, because the limitation of Reynolds number to determine the laminar and turbulent is different compared with the application. So for example, in this situation, so the situation is flow in pipe. Flow in pipe. So the velocity, the equation for the number is rho Vd over mu, which is the d is the diameter of the pipe. And then we found that if the Reynolds number less than 200, so it is fully laminar, and if the Reynolds number is more than 4,000, so it is fully turbulent. So between 2,000 and 4,000, so it is a transition region. So and then, but this is for the ideal condition, means if the surface is very, very smooth, so we assume that there is no disturbance on the surface, then we could assume that this is the most correct one, and the most nearest the result that can be compared with the experimental one. So if we have a disturbance, so means your roughness of your pipe is rough, and so on and so forth, maybe these terms cannot be used. So for example, another application, we discussed it previously. For example, we have an open channel. Okay, in open channel, so means that we have a conduit like this one. So means that we have a surface that contact with atmospheric pressure here. So let's say we have a drainage like this one. So the limits, yes, we could calculate by using the Reynolds number. So but the Reynolds number will become rho v r h over mu, where the r here is the hydraulic radius of this conduit. So and then the limit is also changed, mean the Reynolds number less than 500 is considered laminar, but Reynolds number more than 2000, so it's considered fully turbulent. So it's depend on what application you have. Okay, and then we are focusing on boundary layer. So let's say we have a boundary layer here. So and then we have the laminar, and then we have a transition, and then we have a turbulent. So the transition here means when the laminar boundary layer change to turbulent boundary layers. But in a real application, normally people will say, we will assume that the transition region for boundary layer is quite short. So we assume that sometimes we neglect. So at this point, we neglect the transition region. Then so we could say that the region here is Reynolds number greater than 5 times 10 by the power of 5 is fully turbulent. So less than this, so we can consider as a laminar boundary layer. And the equation to calculate the Reynolds number for flat plate like this one, so is Reynolds number equal to rho v L over mu. So mean L here is the length of this length of the plate, or the x-axis here. In certain textbook, they will write as rho vx over mu. Okay. So and then if you read about boundary layer, you will find that the surface roughness here is actually become the important parameter to determine the Reynolds number. In smooth surface, for example, you are using glass, for example, a very smooth surface. So maybe your Reynolds number, the transition is say is 1 times 10 by the power of 6. We could consider that. So it's changing actually. After this, we will see more about boundary layer and so on. So you will find that it is depend on the experimental work, because it is not easy to determine it by only with one single numbers. So this is actually the what we talk about. So we have a laminar here. So and then we have a transition, and then we have a fully turbulent. So actually it can be done. It can be observed from the experimental. So I hope you could read our textbook, Viscous Split Flow, or you could surf in Google. Google will show you a lot of images that shows the what happened when the laminar changed into the turbulent boundary layer. So in laminar here, we found that there is no pattern of flow. So that is the very simple definition about the laminar flow, because you know laminar means all the molecule flow in their own path. They will not cross each other, and they will easily to be determined as equation or function of that flow. So mean the molecule is flow move in their own path, their own traffic. So there is no accident there. So and then when the velocity start to increase, so the basic explanation that you could understand is not all the molecule with will flow at will increase their speed. So means that at transition here, so you will find that the molecule one might be molecule here is remain at the at its previous speed, but molecule here is now moving at certain higher speed. So when the changes of velocity occur, so or the increment of velocity for each molecule increase rapidly, so it will to make sure that the molecule can move forward, so it needs to change the path. So when it's changed the path, so means it start to create a chaotic pattern of flow. So start that moment, so the turbulence start to occur. So and then it's occur, it start to give us slightly unpredictable pattern. So and then finally it will become fully turbulent. In fully turbulent, it is difficult for us to detect the pattern. Why? It's back to the idea of this one. So means that if your flow is too high, the velocity is too high. So if you put an ink here, so immediately it will uh, uh, absorbed by the ink will be absorbed by the turbulence, so it's the color of the ink will disappear immediately. Okay, something like this. So in fully turbulent, it is not easy to find the patterns, because the flow is totally chaotic, so it's become see-through again. So and then I hope you could read this one, especially in our textbook here. So I could show that we could see a pattern here to see the transition between laminar and turbulent. So here it says that the transition may be occur at 800,000, so mean 8 by 10 by the power of 5. Okay. Now, so for the transition here, so what I do is I give you all the equation, and then we go for the tutorial, because I think it is easier for us to understand how to solve the what happened in the transition by having the tutorial, instead of we are going to derive equation and so on, so forth. So but the few equation that we use here is simplified in this slide. So first, I hope you could understand, you could remember the Fagner-Scan solution. However, you are quite lucky, because in this COVID era, COVID period, the test will be open book test. So you may refer to this table. If not, you need to remember all this equation. So we are using Fagner-Scan solution, and Fagner-Scan solution is shown in this table. So as I said previously, Fagner-Scan equation is actually derived from the Blasius. So Blasius is for the flat plate, but for Fagner-Scan, they try to derive, they use the same idea of Blasius, but they put the parameter of m and beta. And beta is showing the angle of a slope. So, and then if you go through our textbook, you will find that Blasius used in this textbook is this term, eta is equal yu over 2 nu x, and the Fagner-Scan will using this one. So eta equal n plus 1 over 2u over x. So it plus terms here, n plus 1, to reflect the angle or the inclined slope. So, and then the m here can be the relation between m and beta is shown in this equation. So, and then if this is the equation of the theta, so I think you still remember we calculate the momentum thickness by using the this idea. We have f prime 1 minus f prime and so on. So, and then the momentum thickness for Fagner-Scan, so it's showing by m star here, just to differentiate between the Fagner-Scan idea and Blasius idea, is showing like this one too. So means it in simple idea. So it takes this equation to calculate Fagner-Scan momentum thickness, but we add m plus 1 here, okay, to show the effect of a slope. So the most common one is actually the Fagner-Scan solution and the Thwaite solution. So we have this Thwaite solution, because Thwaite solution can be used to predict the separation. Separation means that the boundary layer is detached from the surface of curved object that we have, and sometimes it can be used to predict the value of theta. We have a theta here, so we need to use the theta. Then we could substitute with Fagner-Scan equation or other equation that I'm going to show you later on to know or to predict the transition area, or to predict the stability of flow. So another equation that easy to solve, because if you read the textbook, it's found that sometimes we need to do the numerical. We need to substitute into equation, and we need to give all the parameters, and then you withdraw a graph. That's why I will skip a certain subchapter in our textbook, because we cannot conduct that in classroom. So it's more on your research work. Okay. Please remember that this subject has a final exam. So if we don't have any COVID problem, so you will have a final exam and so on and so forth. That's why we designed this course to make sure that students could answer by in final exam. So we try to neglect all the numerical works or problem that ask student to use a certain software. So the Michel solution is quite a little bit can be done in a classroom. So we take a Michel solution. So I just give you a few equation here. So, and then we have the Wazan solution, and then we have a Venn Dries solution, and we have a Dunham solution. We will see all the solution, a few tutorial about this. So I hope you could understand the solution. So I will show it step by step in this video.